In the previous section, we talked about Euler circuit problems in general, just kind of an overview. We're going to take a step back in this next section and talk about what a graph is, and later we're going to use the graphs to solve the Euler circuit problems. Okay, this section is really, sorry, it's just a lot of vocab, okay, this section and the next section as well, but it's important to know this stuff because we're going to be using it in the following sections when we're solving the big problems. A graph, it's just a structure that defines pairwise relationships within a set to objects. So the objects themselves are the vertices, so like little dots, and then the pairwise relationships are the edges, so the lines connecting the dots. It's as straightforward as that. So if x is related to y, if and only if xy is an edge. So to illustrate that really quick, let's say I have a point. Here and a point here, and this one is x and this one is y. Okay, those are the vertices. They have a relationship. So x is related to y, or y is related to x, if and only if we have an edge connecting them. So xy would be the edge in this case. So we have, of course, the vertices, which are the dots, and the edges, which are just the lines. And they don't have to be straight lines, they can be curved, but they do have to connect two vertices together. So I can't have, for instance, I can't have this. This wouldn't work. So I'd have to have a vertice, or I'd have to have a vertex on the opposite end of this line. So, no. Alright, this graph has 6 vertices, so notice all the dots, A, B, C, D, E, and F, and 8 edges. And notice that some of the edges are not straight, just like the previous slide said, that it's okay to have curved edges, and we even have a loop in here. We're going to talk about that in just a minute. So the edges can be described by giving the two vertices that are connected by the edge. So, for example, edges are, here I'm going to highlight these. So AB, that is an edge, okay? AD is another edge. BB, and BB is kind of interesting because it starts and ends at the same place. So here, let me erase what we have already, because BB is a little different. So B starts at B and then, well, ends at B. So that would be BB. And we have the others, so like CD and CD again. So you can call that DC or CD. Really doesn't matter. Alright, first note that the point where the edges BE and AD cross is not a vertex. Okay, so this particular point right here, it's kind of like they're going on top of each other and not actually touching each other. Second, vertex F is not connected to any other vertex, so we're going to call it vertex F an isolated vertex. So if these were islands with bridges, and F is an island, there's no way to get over to island F. And the last thing, third, note that this graph has a loop named BB, and we've already kind of talked about that here, and I'll illustrate that once again. So B ends back at B, that's what we call that BB. It is permissible to have two edges connecting the same two vertices, as in the case with CD. So again, we kind of already looked at that a couple slides ago. So CD and CD here, that is okay. When a graph has more than one edge connecting the same pair of vertices, it is said to have multiple edges. So pretty straightforward. Okay, here we have a better real-world example. So this is one giant graph. It's actually a disconnected graph because we have these two separate components. So here's one component of the graph, and here's another component of the graph. You can make up whatever you want for this kind of situation. maybe we have a group of friends that have dated within their circle of friends. So for instance, uh, Meg has dated Moose, and Moose is the only boy Meg has dated. But Moose has also dated Ginger and has also dated Betty. Whereas Betty has dated Jughead and Reggie, and Ginger has dated Jughead and Moose. What a hot mess here. And then over on the other side, Veronica and Archie, they're happy. There's no drama here. They're only ever dated each other. So that's one way we can put it. And here we have something kind of weird. It's just a graph with no edges. It is possible, not always the most useful thing, though. But in this case, every vertex would just be called an isolated vertex. Now let's try to draw a picture, given some vertices and edges. So consider the graph with vertices K, R, S, T, and W. And I'm just going to draw these in random spots because it really doesn't matter what the graph looks like as long as everything is connected properly. So we have, here I'm just going to draw 5 dots. Okay, that works. And each one of these, we have K, R, S, T, and W. Alright, now the edges are represented by RS, so R and S are connected. We have RT, TT, so in that case we're going to have a loop TS, SW. WW, we have another loop, and WS. So WS, we're going to have those multiple edges there. So there's 2 times where W and S are connected. And notice that K is out there alone as an isolated vertex.